Hello everyone, welcome to this video where we'll explore one of the foundational aspects of working with PySpark, how to create a data frame in PySpark. Data frames are the backbone of data processing in PySpark, offering a structured and an efficient way to handle large data sets. Whether you're starting with Python objects like lists or pandas data frames or reading from files like CSV, JSON, or Parquet, PySpark provides multiple ways to create data frames tailored to your needs. In this video, we'll walk through these methods step by step so you can master the art of creating data frames in PySpark. Let's get started. Introduction. In PySpark, a data frame is a powerful abstraction used for organizing and processing data. It represents a distributed collection of data structured into named columns, much like a table in a relational database or a data frame in pandas. Data frames are one of the most popular and versatile features in PySpark, offering a high-level, intuitive interface for data manipulation, analysis, and processing. With support for various file formats, schemas, and SQL-like operations, PySpark data frames are essential for handling large-scale datasets in a distributed environment efficiently. Ways to create a data frame in PySpark using multiple methods. 1. From a Python list. Creating a data frame from a Python list of tuples is one of the simplest and most intuitive ways to work with PySpark. By defining your data as a list of tuples and specifying column names, you can easily transform it into a structured data frame. This method is especially useful for small datasets or when prototyping and testing PySpark applications. It provides a quick way to create and manipulate data while leveraging PySpark's distributed processing capabilities. Practical example. This example demonstrates how to create a data frame in PySpark using a Python list of tuples, which is one of the most straightforward and commonly used methods. Let's break it down step by step. The process begins with the initialization of a Spark session, which serves as the entry point for all PySpark applications. The Spark session.builder.appName created data frame method sets up the session and assigns it a name. Created a data frame for easy identification in logs or monitoring tools. The getCreate method ensures that a new Spark session is created if one does not already exist. Next, the data is defined as a list of tuples, where each tuple represents a record. In this example, the data consists of three records: Alice 30, Bob 25, and Charlie 35. Each record contains a name and an age, which correspond to the two columns in the data frame. The column names are specified as a Python list name age. These names define the schema for the data frame, providing meaningful labels for the data fields. The created data frame method is then used to convert the list of tuples into a PySpark data frame. This method takes the data and column names as input, creating a structured, distributed dataset that can be processed and analyzed efficiently. Finally, the df.show method is called to display the contents of the data frame in a tabular format. For this example, the output will show three rows with two columns, name and age clearly presenting the structured data. This example highlights the simplicity and power of PySpark's API for creating and handling structured data, making it a foundational tool for big data processing and analysis. 2. From a dictionary. Creating a data frame from a Python dictionary in PySpark involves using the row class to map key value pairs into structured rows. This method is useful when working with nested or labeled data, as dictionaries naturally provide a schema-like structure. By converting dictionaries into rows, you can create a PySpark data frame that maintains the key value relationships as column names and values. This approach is particularly effective for transforming semi-structured data into a format suitable for distributed processing and analysis. Practical example. A This example demonstrates how to create a data frame in PySpark using the row class, which is particularly useful for transforming data from dictionaries or other structured sources into a tabular format. Let's break it down step by step. The data is first defined as a list of row objects, where each row represents a record in the data frame. The row class in PySpark allows you to create structured records by assigning column names as keys and their respective values. In this example, they the first row is created as row name Alice, age 30, representing a record with a name column containing Alice and an age column containing 30. Similarly, the second and third rows are created for Bob and Charlie with their respective ages. This structure is particularly useful when the data is naturally organized as key value pairs, such as JSON or nested dictionaries, as the row class mirrors the structure of a table's rows and columns. The created data frame method is then used to convert the list of row objects into a PySpark data frame. Since the row class explicitly defines the schema, the data frame automatically inherits the column name's name and age and their respective data types. Finally, the df.show method is called to display the data frame in a tabular format. The output will include two columns, name and age with the respective values for each record displayed as rows. This approach is particularly useful when working with datasets that are naturally represented as dictionaries or key value pairs, allowing you to leverage PySpark's distributed processing capabilities while maintaining a clear and organized schema. 3. From a CSV file. Creating a data frame from a CSV file is one of the most common methods for loading data into PySpark. Using the spark.read.csv method, you can directly load a CSV file into a structured data frame. This approach is ideal for processing large datasets stored in CSV format, as PySpark automatically handles distributed reading and can infer the schema or use specified column names. With options like specifying headers, delimiters, and handling null values, this method provides flexibility for efficiently working with structured data stored in CSV files. Practical example. This example demonstrates how to create and load a PySpark data frame from a CSV file in a distributed environment using Databricks file system DBFS. It combines the use of pandas, DBFS, and PySpark to efficiently handle structured data. Let's go through the steps in detail. Step 1. Create a CSV file and save it to DBFS. The data is initially created as a Python dictionary representing employee details such as ID, name, department, salary, and joining date. This dictionary is converted into a pandas data frame, which is then saved locally as a CSV file using the to_cs method. The file is temporarily saved at /tmp/employees.csv on the local file system. To make this CSV accessible to PySpark in Databricks, it is uploaded to the Databricks file system DBFS using details.fs.cp. This utility copies the file from the local system to DBFS at the path dbfs:/tmp/tmp/tmp/v, ensuring that the file is accessible within the distributed environment. A confirmation message prints the location of the uploaded CSV file. Step 2. Initialize Spark session. A Spark session is initialized to enable PySpark operations. The builder.appNameCreateAndReceive method assigns a name to the session, and getOrCreate ensures that the session is created or retrieved if it already exists. And this session serves as the interface for creating and managing PySpark data frames. Step 3. Read the CSV file into a PySpark data frame. The CSV file is loaded into a PySpark data frame using the spark.read.csv method. The header true parameter specifies that the first row of the CSV contains column names and infer schema true automatically infers the data types of the columns based on the values. This step converts the structured data in the CSV file into a distributed data frame that PySpark can process efficiently. This is step 4, show the data frame. The df.show method is used to display the contents of the data frame in a tabular format. This provides a quick overview of the data, including all columns and sample rows, making it easy to verify that the data has been loaded correctly from the CSV file. Step 5, print the schema of the data frame. To understand the structure of the data frame, the df.printSchema method prints the schema showing the column names, data types, and whether null values are allowed. For example, ID is inferred as an integer. Name and department are inferred as strings. Salary is inferred as an integer. Joining underscore date is inferred as a string. This schema validation ensures that the data types are correctly interpreted, which is critical for subsequent data transformations and analysis. This approach highlights how PySpark simplifies the process of loading and processing structured data from CSV files in a distributed environment, making it highly efficient for handling large-scale datasets. 4. From a JSON file, creating a data frame from a JSON file is a straightforward way to handle semi-structured data in PySpark. Using the spark.read.json method, you can load JSON files directly into a PySpark data frame, with Spark automatically inferring the schema and organizing the data into columns. JSON is a widely used format for data exchange, and PySpark's ability to process it efficiently makes this method ideal for applications like log analysis, API data processing, or working with nested and hierarchical datasets. With its support for distributed processing, PySpark ensures that even large JSON files can be processed seamlessly. Practical example. This example demonstrates how to create and load a PySpark data frame from a JSON file, which is a common format for handling semi-structured data. It showcases the process of creating a JSON file, reading it into a PySpark data frame, and inspecting its structure. Let's go through the steps in detail. Step 1, create a JSON file. The data is defined as a list of Python dictionaries, where each dictionary represents a record with fields such as ID, name, department, salary, and joining underscore date. This structure reflects the schema of the data and is well suited for conversion to JSON. The data is then saved to a JSON file named employees.json using Python's built-in json.dump method. The indent4 parameter ensures that the file is formatted for readability, making it easier to verify the content. The resulting JSON file is stored locally and its path is printed for reference. Step 2, initialize Spark session. A Spark session is initialized, which serves as the entry point for interacting with PySpark. The session is named RedZone example for easy identification in logs and monitoring tools. This session enables reading the JSON file and transforming it into a distributed data frame for processing. Step 3, read the JSON file into a PySpark data frame. The JSON file is loaded into a PySpark data frame using the spark.read.json method. The file path is specified using the file protocol to ensure compatibility with local file systems. The multi-line true parameter is crucial here, as the JSON file contains an array of objects requiring PySpark to pass the file correctly as a multi-line JSON. PySpark automatically infers the schema of the JSON file, mapping the keys in each dictionary to column names in the data frame and assigning appropriate data types based on the values. Step 4, show the data frame. The df.show method is called to display the contents of the data frame in a tabular format. Each record from the JSON file is represented as a row in the data frame, with columns corresponding to the keys in the JSON objects. For example, the Idaho column contains integers, the name and department columns contain strings, the salary column contains integers, the joining underscore date column contains strings representing dates. This step confirms that the data has been successfully loaded into the data frame. Step 5, print the schema of the data frame. The df.printSchema method provides a detailed view of the data frame structure. It lists each column name, its data type, and whether it allows null values. For instance, ID is inferred as an integer long type. Name and department are inferred as string type. Salary is an integer. Joining underscore date is a string. This schema validation is essential for ensuring that the data types align with the requirements of subsequent transformations or analysis. This example highlights the power and flexibility of PySpark for working with JSON files, enabling efficient handling of semi-structured data at scale. 5. From an RDD. Creating a data frame from an RDD resilient distributed dataset allows you to leverage the structured capabilities of a data frame while starting with the more flexible RDD. In PySpark, you can convert an RDD into a data frame by defining a schema explicitly or allowing PySpark to infer it. This method is particularly useful when working with unstructured or semi-structured data that needs to be transformed into a tabular format. By combining the raw processing power of RDDs with the analytical features of data frames, you can efficiently handle complex data processing workflows. Practical example. This example demonstrates how to create a data frame from an RDDD resilient distributed dataset in PySpark. By converting an RDDD into a data frame, you combine the flexibility of RDDs with the structured data processing capabilities of data frames. Let's break this process into steps. Step 1, create an RDD. The data is first created as a list of tuples with each tuple representing a record. In this case, Alice 30 represents a record with the name Alice and an age 30. Similarly, tuples for Bob and Charlie are included. The list is converted into an RDD using spark.sparkContext.parallelize, which distributes the data across the Spark cluster. RDDs are the foundational abstraction in Spark, representing distributed collections of objects that can be processed in parallel. Step 2, define the schema. A schema is defined by specifying the column names as a Python list name age. These column names will be assigned to the respective fields in each tuple. Defining a schema ensures that the data frame has meaningful column names and a structured format. Step 3, convert RDD to data frame. The toref method is called on the RDD, passing the schema column names as an argument. This method transforms the RDD into a data frame where the tuples are treated as rows and the schema defines the column names. Data frames provide a higher level abstraction over RDDs, allowing SQL-like operations and optimizations. Step 4, display the data frame. The df.show method displays the contents of the data frame in a tabular format. Each tuple from the RDDD is converted into a row, and the schema defines the column headers. The name column displays Alice, Bob, and Charlie. The age column displays their respective ages. This example highlights the ease of transitioning from RDDs to data frames in PySpark, enabling you to work with raw data in a distributed environment while leveraging the powerful features of structured data processing. 6. Using explicit schema. In PySpark, you can create a data frame by defining an explicit schema using struct type and struct field. This approach gives you full control over the structure of your data frame, allowing you to specify column names, data types, and whether null values are allowed. Explicitly defining a schema is especially useful when working with unstructured or semi structured data, as it ensures consistency and accuracy in data processing. This method is ideal for scenarios where schema inference is insufficient or when you need to enforce a specific structure for downstream operations. Practical example. This example demonstrates how to create a PySpark data frame with an explicit schema using struct type and struct field to define the structure of the data frame. Explicit schema definition provides precise control over the column names, data types, and nullability, ensuring the data frame is structured exactly as required. Let's go through the steps in detail. Step 1, define the sample data. The data is represented as a list of tuples where each tuple contains two values, a name and an age. For example, Alice 30 represents a record with the name Alice and the age 30. Similarly, other records are provided for Bob and Charlie. This sample data forms the foundation for the data frame. Step 2, define the schema. The schema is explicitly defined using struct type, which is a collection of fields, and struct field, which specifies the details of each column. Struct field name, string type, true defines a column name of type string type, allowing null values true. Struct field age, integer type, true defines a column named age of type integer type, also allowing null values. The schema ensures that the data frame has a predictable structure regardless of the input data. Step 3, create the data frame. The created a data frame method is used to convert the sample data into a data frame with the defined schema passed as an argument. PySpark uses this schema to interpret the data and enforce the specified structure. Unlike schema inference, this approach guarantees that the data types and column names are explicitly set. Step 4, display the data frame. The df.show method is called to display the contents of the data frame. The output appears in a tabular format with two columns. The name column displays the names Alice, Bob, Charlie. The age column displays the corresponding ages 30, 25, 35. This approach highlights the flexibility and power of PySpark in handling structured data, enabling you to create data frames tailored to specific requirements with precision and reliability. 7. From a Parquet file. Creating a data frame from a Parquet file is one of the most efficient ways to handle structured data in PySpark. Parquet is a columnar file format optimized for big data processing, offering high performance for both read and write operations. It supports efficient compression and encoding schemes, which reduces storage requirements and speeds up query execution. Using the spark.read.parquet method, you can load Parquet files directly into a PySpark data frame, making it an ideal choice for scalable and high performance data workflows in distributed environments. Practical example. Like, this example demonstrates how to work with Parquet files in PySpark, showcasing the process of saving a data frame as a Parquet file and then reading it back for further operations. Parquet is a highly efficient columnar storage format designed for big data processing, offering fast reads and writes with excellent compression capabilities. Let's break down the steps in detail. Step 1, initialize Spark session. A Spark session is created to enable PySpark operations. The builder.appName readParquetIc sample method assigns a name to the session for identification, and get.create initializes the session. This Spark session serves as the starting point for creating and manipulating data frames. Step 2, create a data frame. The data is defined as a list of tuples with each tuple representing a record containing fields such as ID, name, department, salary, and joining underscore date. Column names are specified as a list ID, name, department, salary, joining underscore date. Using the created data frame method, the data is transformed into a PySpark data frame df underscore original. Step 3, save the data frame as a Parquet file. The write.parquet method is used to save the data frame as a Parquet file in dbfs databricks file system at the specified path dbfs:/tmp/employees.parquet. The mode override ensures that any existing file at the path is replaced. Saving data in Parquet format optimizes storage and retrieval for big data applications. Step 4, read the Parquet file. The Parquet file is read back into a PySpark data frame using the spark.read.parquet method. This step highlights the interoperability of PySpark with Parquet, enabling seamless data exchange between storage and processing layers. Step 5, show the data frame. The df.show method is called to display the contents of the data frame, showing all records and columns. This step verifies that the data has been successfully loaded from the Parquet file. Step 6, print the schema. The df.printSchema method provides a detailed view of the data frame structure, including column names and their data types. For example, ID is inferred as an integer. Name and department are inferred as strings. Salary is an integer. Joining underscore date is a string. The schema validation confirms that the data types align with the original data frame. Step 7, perform operations on the data frame. Several operations are performed to showcase the analytical capabilities of PySpark. Filter employees with salary 6,000. Using the filter method, rows where the salary column exceeds 6,000 are selected. The resulting data frame is displayed, showing only employees meeting this criterion. Group by department and calculate average salary. The group by department.ab salary operation groups the data by the department column and calculates salary for each department. This operation demonstrates PySpark's ability to perform aggregations on distributed data efficiently. This example illustrates the efficiency and flexibility of working with Parquet files in PySpark, demonstrating how they enhance performance and scalability in data engineering tasks. Using pandas data frame. Creating a PySpark data frame from a pandas data frame is a convenient way to transition from smaller scale data manipulation to distributed big data processing. Using the created data frame method, you can convert a pandas data frame into a PySpark data frame, enabling it to leverage Spark's distributed architecture for large data sets. This method is particularly useful when prototyping or working with smaller data locally in pandas and then scaling up for larger workloads in PySpark. It combines the simplicity of pandas with the scalability of PySpark, making it an effective workflow for data analysis and processing. Practical example. This example demonstrates how to create a PySpark data frame from a pandas data frame, which is a useful technique for transitioning from local data manipulation to distributed big data processing. By converting a pandas data frame to a PySpark data frame, you can take advantage of Spark scalability and distributed computing capabilities while starting with the simplicity of pandas. Let's break this process into steps. Step 1, create a pandas data frame. The data is initially created as a pandas data frame, which is widely used for small scale data manipulation in Python. In this case, the name column contains the values Alice, Bob, Charlie. The age column contains their respective ages 30, 25, 35. The pd.dataframe function is used to construct the pandas data frame PDF, which holds this data in a tabular format. Step 2, convert the pandas data frame to a PySpark data frame. The pandas data frame is converted into a PySpark data frame using the spark.createDataFrame method. This method takes the pandas data frame as input and transforms it into a distributed PySpark data frame DF. During this conversion, PySpark automatically infers the schema based on the data types in the pandas data frame. The name column is inferred as a string. The age column is inferred as an integer. This step enables the data to be processed in a distributed environment, making it scalable for larger workloads. Step 3, display the PySpark data frame. The df.show method is called to display the contents of the PySpark data frame in a tabular format. The output includes two columns, name and age, with the corresponding values for each record. This step verifies that the data has been successfully converted from pandas to PySpark. This example highlights how PySpark's integration with pandas provides a smooth and efficient way to scale from small to large datasets, leveraging the strengths of both libraries. And that wraps up our exploration of creating data frames in PySpark. As we've seen, PySpark offers a variety of ways to create data frames, whether it's from Python objects, files, RDDs, or even pandas data frames. Each method is designed to handle different use cases, making PySpark a versatile tool for data processing. If you found this video helpful, don't forget to like, share, and subscribe for more tutorials on PySpark and big data analytics. Thanks for watching and see you in the next video.